Hello everyone, this is lesson 6 of unit 2 on electric force and fields. This one's about potential difference and electric fields. So example number 1 here, we've actually got 4 examples this time, but example number 1, we have a situation where we have parallel plates, good old parallel plate situation. This time we're given some different values between the plates. So we're told that there's a 2 centimeter mark where it looks like P is located, and then 3 centimeters between P and Q. It's worth mentioning the assumption, but of course the difference between this position of Q and if I was to make another position of Q over here, this difference would be 0. This would be equivalent to carrying a heavy object. So if this is you walking along and you're carrying a heavy object, it might feel like you're doing lots of work, but if the object itself only moves horizontally and the object ends up over here, if there is no change in the height, in other words, if this height is the same as this height, then even though it feels like it's heavy and you're doing lots of work, actually, in terms of physics, you've done no work whatsoever because there's been no force applied for a distance, assuming, of course, that you're going a uniform, if this is a uniform velocity, if this is uniform, okay, you're not accelerating, you're just moving at a constant speed, then there's been there's no air resistance, all of those kind of assumptions, then you've done actually no work. And the same thing can be said here in parallel plates. The analogy continues from gravity to electric fields. If you were to take a charge, and let's say it's this position Q, if you were to move it horizontally along here to this position, then no work has happened, there's been no change in potential, etc., etc. So the only thing we're interested in, just like with gravity, is the difference perpendicular to the alignment of the plates. In other words, the change in position parallel to the electric fields. Okay, so we're just asked to consider the electric field. So let's go ahead and put some values on here, or some field lines on here. First of all, it's worth noting that, of course, the large side of the battery is going to be our positive side. So here it is. And then this means this side is negative. Of course, electric fields by convention always are drawn from positive to negative. So we would draw our field being uniform within these parallel plates like this. As we get towards the end, we start seeing curvy lines like this, which is why we are going to sort of ignore the edges of a parallel plate system, and we're only going to focus on the middle bit. So you should, so in any parallel plate system, we tend to avoid putting charges near the edges because then we're not sure if it's uniform. So one of the beauties of a parallel plate system is that we can assume this uniform electric field in between. And that's the key to this question. It's kind of a hint. We're asked to determine the electric field at locations P and Q. Well, what do we know about electric fields? We know that we can say an electric field in absolute lines. This means it's going to be a positive. Well, we ignore the positives and negatives and absolute values. So the electric field here is either going to be the force electric over a charge, which would be the units newtons per coulomb, or we could talk about voltage over distance, which would be volts per meter. Both of these are legit for electric fields. So what do we know? Well, here's our information. We know 72 volts is applied between the two plates, and then we know that we have a cumulative distance between the plates of 6 centimeters. So there's our electric field, uniform electric field. It's going to be 72 volts divided by, well, I've got to be in meters, so 6 centimeters is 0.06 meters. So that means I've got an electric field of 1.2 times 10 to the 3, and I'll call this volts per meter. In other words, 1.2 kilovolts per meter. Now, what's the difference? And so that would be the field strength at Q here. What would be the field strength at P? Well, it's a uniform electric field, so it's kind of a trick question. It's going to be the same. Okay, so example 2, now we do have some calculations to make. We have an alpha particle. So here's our alpha particle in the middle. It's got a charge of +2, so don't forget that this is going to be 2 elementary charges. I got to keep track of my positives and negatives. This is the positive side of my battery, so the top plate's going to be positive, bottom plate's going to be negative. So this alpha particle is moving towards the positive plate. Now, do you think it wants to move towards the positive plate? Not really. It's going to take some work to do that. Or it's going to take some force to do that. So this is where we think about our 2 different systems. So I'm going to try and use different colors to do this. First of all, I mentioned work. We're going to have to do some work to move that alpha particle towards the positive plate. It's going to go from a lower energy state here. Energy is low here. And as it moves towards the positive plate, we increase the potential energy. So to increase the energy, I have to do some work. So I'm going to think about work. The other thing that I'm going to have to think about is a force. Okay, if I'm going to move this thing, I've got to apply a force to it. So we're going to talk about work. And of course, work is intricately linked to energy, the work energy theorem. And so this is kind of the clue. We've got 2 different ways of calculating this, and it's really important that you get used to doing both. And certainly when you see these kind of questions, you're going to think about both of these types of physics principles. So let's go ahead and do the work one to begin with. We've got a change in energy, okay? And you'll remember from your data booklets that we define a voltage, or at least we define a change in voltage, to be a change in energy divided by a charge. And so then that tells us that we can define a change in energy to be a change in voltage times Q. So if I'm doing work, there's going to be a change in voltage, okay, because there's a change in energy. And if I multiply it by the charge, that is the change in energy. Okay, so is there going to be a change in voltage? Well, hopefully you can see that yes, there will be. If I was to take a multimeter and put it here, and I'm going to connect it to my voltmeter and put it here, that's going to give me a value, okay? But if I was to then move that voltmeter a bit closer, so if I was to now disconnect it and then reconnect it a little bit closer, so here, this voltage is going to be different. I'm going to get a smaller voltage because I've got less distance between the plates. So this is a change in voltage. And if I have a change in voltage, I'm going to have a change in energy. All right. Okay, so I'm told that the minimum energy to move this particle is 9.0 times 10 to the negative 17. So that's going to be my change in energy. So I'm just going to put that in here. So 9.0 times 10 to the negative 17 joules is going to be equal to VQ. So if I was to divide this energy by Q, which by the way is going to be 2 times the elementary charge, to the negative 19 coulombs. If I was to do that, I'm going to get the voltage, or the change in voltage, I should say, delta V. I'm going to get the change in voltage from here to here. In other words, a gap of 18 centimeters. Okay. Once I know that voltage, I can just then extrapolate it up to this gap to get the total PD across the total potential difference across the 2 plates. So let's go ahead and get this change in voltage. Okay, so this is my change in voltage from here to here, because I've been given that energy for this alpha particle to move this 18 centimeters. So I get a value. I'm going to get a value here of 281. If I put this into my calculator, 28125. That's the voltage, that's the change in voltage as I move this alpha particle. And now I'm going to divide that per centimeter. So it moved 18 centimeters. Okay, it's moved 18 centimeters. So centimeters. That tells me that for every centimeter in this particular system, for every centimeter, I'm going to have 15.625 something volts. That's going to be volts per centimeter. Okay, well, how many centimeters do I have in total Well, 24. So now all I have to do is take this value, so 15.625 volts per centimeter, and multiply it by the total number of centimeters, which is 24. Okay, the centimeters cancel out, and I'm left now with total voltage across the entire gap of 24 centimeters, which is 375 volts. I'm just going to check my significant digits. I've got 1, 2, 3, 1, 2, 3, 1, 2, 3. So I'm good there with my 1, 2, 3. So let's see if we can do it for force. What do we know about force? Well, there's a little bit of a connection to energy, because of course, the other thing we know from our work energy theorem is that work is a force multiplied by a distance. Okay? And in other words, okay, this is our delta energy. Okay, this is our work energy theorem. And we're told what that value is. We're told that the change in energy is a value in our initial question. So the force acting on this alpha particle in order to get it to move is going to be the work done, or the change in energy. Let's say the work done divided by the distance. In other words, the change in energy divided by the distance. And that change in energy is given, so 9.0 times 10 to the negative 17 joules, divided by the distance. Well, the distance it moved was 18 centimeters, so 0.18 meters. This is going to give me my force, which is 5.0 times 10 to the negative 16 newtons. And we know that the electric field is Fe over Q. So once we have this is the force electric that I have to overcome. So I'm going to put that in and divide it by Q, and that's going to give me the electric field. So plug that into your calculator. You get 1562.5, I think, newtons per coulomb. Okay. Now I need to get the voltage. Well, I also know, this is where our electric field values come in. I know that V over D is going to give me also my electric field. So I can also say that V is the electric field times the distance. And this is the uniform electric field. So it's going to be the same throughout this entire space in the uniform electric field between the two parallel plates. So I'm confident that I can just use this value. And now all I have to do is make sure that I put my total distance between, which is going to be 24 centimeters. So I'm going to say that the voltage across the parallel plates is, well, it's going to be the uniform electric field, so 1562.5 something newtons per coulomb, multiplied by 2 times the elementary charge, so 1.6 times 10 to the negative 19 coulombs. And that's going to give you, surprise, surprise, 375 volts. Notice that they are the same. There are 2 different ways of doing this. Both are very useful. Okay, so example 3, a little bit more going on here. I want you to think about, really at this point, 3 different physics principles that we could potentially use. We've already mentioned the work energy theorem, so let's think about that. Oops, I meant to go delta E. We're also going to think about our forces, so the F net expression. Okay, but we're also going to add one. We're going to say, well, we could also use kinematics. So we've got all of our kinematic equations. Okay, so we'll think about that as well. All of these are in play in these types of questions. It's just a matter of figuring out which one to use. We saw in the previous example that we could use both the work or the force, the dynamic stuff. What we're going to start seeing is that we're also going to be needing to use our kinematics as well. And in the next example, we'll actually see a projectile motion. Okay, so let's think about what we know. We don't know the initial velocity. We do not know Its initial velocity is unknown. What we do know is that it crosses the plates. The electron comes to rest just before it hits the opposite plate. So it's going to come flying through this gap. Here it is. This is the electron. And let's take a look here. This is the large side of the battery. So this is going to be positive and this is going to be negative. So this electron must have enough momentum to make it to the other side. It ends up just resting on the plates over here. But whilst it's doing that, it's going to be experiencing a force, a net force. And that's going to be slowing it down. It's going to be decelerating it. Okay, so if I was to think about this in terms of energies, do I know anything about the initial kinetic energy? No, don't know that. Do I know anything about the electrical energy? Well, maybe. I could say that the electrical energy going from here, just the electrical energy from here to here, that's going to be equal to VQ. So yeah, I could say that. At this point, I would know how much electrical energy it would have at the very end. It would have VQ. But there's not a lot to go on. I only have this one value and I don't know anything else. And what I'm really trying to find is the time it takes. So this may end up being a dead end. But I want you to think about all these things as you're going through these problems. This might be a dead end. We'll come back to it if we need it. But let's think about the forces. And it's totally normal to do this. It's totally normal to look at one way of thinking about a question, get a bit stuck. And if you do, change your tactics, look at a different physics principle. Okay, so remember that this is, if we're talking about work, we're using our physics principles 3 or 5. If we're using our dynamic stuff, then we're using physics principle 0 or 1, depending if there's a net force. In this case, it would be 1 because there would be a net force. It's not balanced. And then if you're using kinematics, it's the same thing. Kinematics would be, again, depending if it's uniform motion or uniform acceleration, physics principle would be 0 or 1, potentially even 2 if it was circular. Okay, and that's going to come into play later on when we get into electromagnetism. But for now, just think about that as you're going through these problems. All right, let's get into potentially using our F-net expression. So let's think, we assuming no air resistance, we're assuming no gravity. So is there an F-net? Well, let's see. What are all the forces acting on this electron? It's definitely got force electric. And that force electric will remain constant because we have a uniform electric field between these plates. So that's a uniform, it's going to be a constant force. And there are no others. We're assuming no air resistance, we're assuming no gravity. And this is going to be a non-zero force. Because it's unbalanced, it's physics principle 1. So we can say that this is going to be ma. Okay, there is going to be an acceleration. And we know the mass of an electron. So that's ma. And we also know that the force electric is going to be equal to EQ. Okay, now let's think about electric field. What do we know about that? Well, that should be ma. What do we know about electric field? We know that it's got 2 units. Okay, remember electric field can either be Fe over Q or V over D. And that's kind of the clue here. We know voltage and we know distance, so that's a little bit of a clue. I'm going to switch out electric field for V over D. So V over D, Q. Okay, so I seem like I'm getting somewhere with this. Let's keep going. I think I can get the acceleration. If I go acceleration of this electron, obviously it's going to be going to the left because my force is going to the left, but the acceleration is going to be VQ over MD. All right? Now, let's think about kinematics. Okay, I've kind of given it away that we're going to be using it. It's going to be accelerating, so I'm going to be using my 5 kinematic equations. And when I have my 5 kinematic equations, there's going to be 5 variables, and what I'm hoping to do is find 3 variables and solve for a 4th. and then I pick which equation I'm going to use. So let's think about what I have. I know that I need time. That's got to be one of my variables. I do not know the initial velocity. I do not know that. So that cannot be part of my equation. I do know the final velocity, it's 0, because it comes to rest. I do know the acceleration, because I just worked that out. It's VQ over MD. And I do know the distance that it's going to travel. It's going to travel, if we say that this side of the sheet is positive, this side of the sheet is negative, just in terms of convention of kinematics, then my displacement is 14 centimeters, so 0.14 meters. Okay, so I can use a kinematic equation. I've got 1, 2, 3 values, and I'm solving for the fourth. That's kind of the rule with our kinematics equations. And so hopefully you can see I'm going to be using my d is equal to VFT minus 1/2 AT squared. Okay, and my VF is 0, so that makes it a little easier. I can rearrange this and say that time, which is what I'm trying to find out, is 2d over a all square rooted. And if I bring in my equation for a, time is 2d squared m over vq square rooted. And if you plug all that into your calculator correctly, you should get 2.73 something something times 10 to the negative 9 seconds. And it's good to remember that anytime you have to the negative 9, that's nano. So let's go 2.73 nanoseconds. All right, guys, last one on this video. This is a long video, isn't it? I know. But fourth example, these are all very, very important. So make sure you understand these. Here we have, again, it's a moving charge in a perpendicular electric field. This time we have our projectile motion going on. So what are we told? Well, we're told that we know the electric field between the plates. We need to determine the vertical displacement. Okay, so assuming that it makes it to the other side, which is here, so we can kind of imagine there's a screen. There's a screen here that detects where the electron hits. We need to know how far away from this central undeflected path. So I'm going to put this undeflected path in. This is undeflected. If there was no electric field, this is where the electron would go. How far along here would it? How far along would it go along the screen? In other words, would it hit here somewhere or here somewhere, and by how much? Well, let's put the field lines in so we can at least figure out which way it's going to go. We're told that the top of the plates are positive, so the field lines are going to go from positive to negative, like this. This is my electric field. It's uniform, which makes it nice and easy. And so this electron, hopefully you can see, it's going to feel a force towards the positive plate. So it's definitely going to be this side of the undeflected path, not this side. The question is by how much? How much is it going to move along this distance here? That's what I'm trying to find out. This value here. Okay, so we got some kinematics going on here. First of all, the only thing we're told is the electric field. So let's think about that over here. We know the electric fields. We know that we can talk about electric fields as forces over charges or voltage over distance. So I'm not sure I know just yet which one I need to do, but I know the value. I know that it's 171 newtons per coulomb. And, well, I think I'm going to go with, let's see if we're going to try and solve for a force, because I know that a force is also equal to mass times acceleration. So maybe I need this acceleration in here, I don't know. Let's keep pursuing this. I know, so there's my electric field. If I multiply my electric field by the charge, which is going to be one elementary charge, so that's 1.6 times 10 to the negative 19 coulombs. If I multiply these things together, I'm going to get the force this electron experiences. In other words, if that was the electron there, it's going to feel this or experience this force. And I know that force is equal to mass times acceleration. So I can say that the acceleration, the uniform acceleration that this electron experiences, is gonna be equal to, if you plug this into your calculator, it's gonna be equal to 3.003 something something times 10 to the 13 meters per second squared. Okay, that's the acceleration it's gonna experience upwards. Okay, so I know the acceleration. I also know the horizontal distance that it travels. So this is where I'm going to start thinking about this as a projectile motion problem. And hopefully you can recall from physics 20, when we have a projectile motion problem, we're going to think about it like this. We're going to say we can think about the X and the Y systems differently. In the X system, we're going to use physics principle 0. In the Y system, we're going to use physics principle 1. In other words, in the X, it's not accelerating. So I'm just going to be using V is equal to D over T. And in the Y, well, it is accelerating, and I'm going to use my kinematics equations, and most likely I'm going to use my D is VIT plus 1/2 AT squared. So let's start putting some values in that we might know. What's going on in the X direction? Well, I know the distance. I know the distance is 40 centimeters. We know the initial velocity. We know that it is 3.1 times 10 to the 6. Let's do that again, 10 to the 6 meters per second. And then we can work out the time. So the time it takes to travel the horizontal distance from here to here is, if you put it into your calculator, 1.29 something something times 10 to the negative 7 seconds. And this is going to be true for both sides of this table. It's going to be true for the X coordinates and true for the Y part of this system. So I can use this time, 1.29 times 10 to the negative 7 seconds. I can use this time on both sides of this table. So I can use it in the Y direction as well. What do I know about the Y direction? Well, I'm trying to find out D. I'm trying to find out the displacement. I know the acceleration is going to be a positive value. The acceleration is going to be up because my force is up. So that's going to be my calculated value from over here, 30 something something times 10 to the 13 meters per second squared. And I know the VI because the initial vertical velocity was 0. Okay, so I'm going to use my D is VIT plus half AT squared formula. So let's just do it down here. D is VIT plus 1/2 AT squared. My VIT is 0. So my D, the vertical displacement at the very end of this system, is 0.25 meters.